Hi, my name's Andrew, and this is Black Holes and Orbits Lab. This lab we had two different parts. Part one, we were finding the mass of a black hole using known values of a star, and then the second part we had a planet, a moon, and a ship, and we had to find the initial velocity of the ship to remain orbit in the system without crashing. In part one, I got the mass as 1 times 10 to the 34th. This makes sense. It's a black hole. It's really big, really massive. That's kind of the point. I'll just explain the process we go down as we go down here. Initial velocity to final velocity. Convert those to momentum. Subtract the momentum. Find the difference in momentum or the impulse. And then we'd find the change in momentum over change in time, which is equal to force net due to Newton's second law right over there. We would find the normal of the P initial, because P initial will have the same direction as motion or as velocity. I guess you could also have put the velocity initial in as well. They would give you the same thing. And then to find magnitude, I just dot product these two, dp and p hat. P hat being in the direction of motion, dp dt not being in the direction of motion, and we're just using the magnitude of that in the direction of p hat. I would rather do that than have to square everything, add them together, then take the square root of that. And then for the parallel direction, it's just p hat times the magnitude in the parallel, the parallel direction. And then it's, as I said before, it's the same thing as force net in that direction. And then that force has to go somewhere, so force perpendicular is just that minus the parallel force. And that's the same thing. And then find the mass of the black hole. We are just doing the magnitude of force net times the magnitude of the star position, because the star position, the black hole position is always at 0, so star position is always the distance between the black hole and the star squared divided by gravitational constant times star m, and that's how I got my equation, or my answer. Okay. The rate of change in momentum is just the effect force has over time, and then the net force is just the instantaneous push or pull that affects the change in momentum. I guess you could say changes a momentum. For part 2, I got a velocity of -2, -700, 0, although it's 2D, so we don't really need to worry about that. There's a lot of extra parts where it did say not to edit. I edited it anyways, because I felt it was unnecessary to have you find the force first, the magnitude, and then get the direction, and then multiply it again, while you can just put it in one big thing and find it. These are just the gravitational forces equations, nothing too special here. All being multiplied by g, the masses divided by the difference of the how far away they are squared, times, this is what's really important, times the position of the moon compared to the position of the object in question. And that would give you these two different forces. You can just add them together. When you go to ship, you can just do the negative of this, Newton's third law, equal but opposite directions. The force of gravity and from the planet on the ship is just another one of these same exact process. Add them together, and then it's kinematics. Find whatever the initial velocity is plus this new acceleration times time. Okay, and what if the system of the black hole, a star, a planet, and a moon? What would we need to know? Well, we would need to know all initial velocities, all initial positions, and all masses, and we should be able to predict a computational model. It looks like I have a little extra time, so I can show you what the models actually look like. I'll just run a little short bit, so I'm still under my little time frame. This is around the black hole, and these vectors do make sense, because if you're in a perfectly circular orbit, the only direction gravity is going to be in is in the direction of the black hole. it's not going to be, there's not going to be any in the parallel direction. As you can see, there was a little bit. Going over here, this is what my end would look like. If you kept going, it would go further, but my computer doesn't really like doing that.